Hello everyone. So let's solve the last set of organic questions from the JAM 2020 question paper, right? So this question says, for the Diels-Alder reaction, question 1 to 4, the activation barriers follow the order. So activation barrier means whichever reaction is fastest, so the barrier is smallest, and if the reaction is slowest, that means barrier is highest. So whichever is easier, that will have a smaller barrier, and whichever is toughest will have the largest barrier. So Diels-Alder reaction. So Diels-Alder reaction, what we know, it is 4 plus 2 pericyclic reaction, right? It's the 4 plus 2 pericyclic reaction. So addition reaction. So if you look here, there are two systems. One is this is one of the reactant which is fixed for all, and then we have to compare between this and this, right? So this is what is called as a dienophile, and these are the systems which is called as diene. So diene, as the name suggests, diene means two alkenes are there which are conjugated to each other, next to each other. So see here there is one alkene, there is another alkene. Similarly, if you look here also, we have this alkene and this alkene. All others are similarly alkenes, so dienes. And this is dienophile. Dienophile means a simple alkene, and dienophile, phile means loving. So because it interacts with a diene, we call it dienophile. So one of the double bond will be reacting with the two double bonds on these systems, and we have to compare. So nothing can be done about dienophile. Whatever has to be done about the diene. Whatever the judgment has to be made based on the diene. Now we know for Diels-Alder reaction, the HOMO of diene interacts with LUMO of dienophile. HOMO means highest occupied molecular orbital. So it needs more and more of electrons. So this acts as a nucleophile, and dienophile LUMO interacts. That means LUMO means lowest unoccupied molecular orbital. So it acts as an electrophile. It accepts electron. So now this cannot be, we cannot do anything about the dienophile. Let us talk about the dienes. So what we need is more and more electrons in the diene, because they will add up nucleophilically, right? And so let's go one by one. So look at this molecule. Now this molecule is not an aromatic system. Why? Because this is not a conjugated system. Here there is a sp2 hybridized carbon, this is sp2 hybridized carbon, this is sp2 hybridized carbon, this is also sp2 hybridized carbon, but this carbon is sp3 hybridized carbon. So it does not have any p orbital which will overlap. So when system is non-aromatic, they are more reactive than aromatic system. Aromatic means they are stable, they will not undergo reaction so easily. And specifically aromatic systems undergo reaction what is called as electrophilic substitution and not electrophilic addition reaction. So for them it will be tough to undergo electrophilic addition reactions, where this will find itself very easy to undergo electrophilic addition reaction. So this will be fastest, and therefore the activation barrier will be lowest. Remember, activation barrier will be lowest. So let us look at it. So either we will have option number C or option number D, because for both of them we have 1 as the last activation barrier. Now let us look between 2, 3 and 4. In 2 we have what is called as furan, and this is thiophene, and this is pyrrole. Now if you look at the aromaticity, furan are least aromatic. You have to remember this when you talk about heterochemistry. This is least aromatic because furan easily undergoes electrophilic addition reaction. Aromatic systems are not supposed to undergo addition reaction, they undergo electrophilic substitution reaction, but this undergoes electrophilic addition reaction, this furan. Why? Because what happens is, this oxygen is there, oxygen is highly electronegative, so it pulls the electron towards itself. So because it pulls its just let me show you what I want to say. See, this oxygen has lone pair of electron. If it has to be aromatic, this orbital has to overlap with this p orbital. That is a p orbital because this is pi bond. So they have to so this orbital has to overlap with this. These two orbitals have to overlap, and this also has to overlap with this p orbital. But the problem with oxygen is very electronegative, and because oxygen is very electronegative, it shrinks, the lobe shrinks because it pulls the electron clouds towards itself, and therefore this lobe becomes very small. And when this lobe becomes very small, its efficiency in overlapping with these p orbitals becomes highly hindered, and because it becomes hindered, they are the system is almost like non-aromatic system, and therefore this will react quite fast. So I have a feeling this should be second least activation barrier, should have the second lowest activation barrier. So 1 and 2, so both C and D still are holding intact. Now let us look at 3 and 4. Now between thiophene and pyrrole, thiophene is more aromatic. Thiophene is more aromatic than pyrrole. Why? Because see, aromatic means it should be very stable, it should not react much. Now sulfur has big lobe here because sulfur is not very electronegative, not as electronegative as oxygen, and therefore this lone pair is there. It should easily overlap with this p orbital of the carbon. But the problem is sulfur has 3 lone pair of electron in 3p orbital, whereas this pi bond is formed because of 2p orbital of carbon. So they don't overlap very well, and because they don't overlap very well, so not lot of electron is available, and therefore they are less reactive. They don't undergo electrophilic substitution reaction faster, and so they are quite stable, and therefore we say they are more aromatic because they are less reactive. Whereas nitrogen has lone pair of electron in 2p orbital itself, and nitrogen is not very electronegative, so the lobe is much larger than what it would have been when it was oxygen. Okay, so this lobe is much larger, and very efficiently and very effectively overlaps with this p orbital of the oxygen, and therefore what happens? Because this overlaps very well with the p orbital of the carbon, of the p orbital of the carbon, lot of electron density is there on the pi bond, and therefore because more electron density is there, I said they undergo nucleophilic addition. So this can go and attack on this side, then this will come and attack on this side, and that's how the reaction happens, and therefore this 4 will be more faster than the third. So third should have third should have highest amount of activation barrier because this will be slowest, and this should be faster, so then fourth should be second. So my guess is third is higher, so third and fourth, so C should be the answer. Let us look into it. So C is the answer. I have gone very slowly, maybe you can pause and read also. Whatever I said is written here. So in Diels-Alder reaction, HOMO of the diene interacts with LUMO of dienophile. You can pause and look at it. I will go slowly once again. Right. Moving on to the next question. The next question is, major product formed for the following reaction is. So we have this alkene, and then cyclohexene, on that we have COOH, and we have I2, sodium bicarbonate and water. So it is very simple reaction of iodolactonization. So they are giving you this product. So they are looking how good are you at stereochemistry, right? Let's move ahead. We'll go step by step. So the first reaction, of course, because double bond is there and iodine is there, iodine undergoes happily electrophilic addition reaction on the alkene. So alkene gives electron to this iodine, and then this I minus leaves, and this lone pair of electrons of oxygen of iodine goes interacts here and you get iodinium ion. Now the important thing is this COH is toward the viewer, that means it is coming outside the board. Your whatever screen you are seeing, this COH is coming outside your screen, and now iodine could have come from front of your screen or could have come behind your screen. Now front of your screen is little tough. Why? Because already COH is there, which is quite bulky. Iodine itself is quite bulky, so they both will sterically hindered. So rather iodine will come from behind, because behind only simple hydrogen is there, which does not create any kind of steric hindrance, and therefore the iodine attacks from behind, and therefore you see this arrow, I have made them dashed arrows, right? And so you get iodinium ion from behind the board. Then you are having sodium bicarbonate. Now sodium bicarbonate, as you know, is a weak base. So weak base, it will remove this proton from carboxylic acid and you get CO minus. Now what happens? This is what they are looking. You have to understand. Here is what comes, what is called as Baldwin's rule. So now CO minus can attack either on this carbon or on this carbon, right? So let us count the number 1, 2, 3, 4, 5. If the attack happens on here, we call it 5 attack, right? Whereas if attack happens on here, then what happens? So it is 1, 2, 3, 4, 5 and 6. So this is called as attack and position number 6. So that's how we number them when we talk about Baldwin's rule. So you understand, attack would have happened on what is shown in the blue arrow, that would have been attack 5, and it could have happened here on the what is shown from the green arrow, that is called as attack on carbon number 6. So it is 6 attack. Now Baldwin's rule, please go and Google Wikipedia, it is there, a nice table is there. Baldwin's rule talks about which attack is favored and which attack is not favored. Now there is something called as concept of exo and endo, tet, trig and dig. So when the attack happens on a sp3 hybridized carbon, so this carbon is sp3 hybridized, you can see it has 4 bonds, 1, 2, 3 and 1 hydrogen is there. So the shape will be tetrahedral, so that is called as attack is on tet. Whereas if attack is on double bond, it is called as trig. Trig means trigonal planar, because when you have double bond is sp2 hybridized and the shape will be trigonal planar, and when triple bond is there we call it dig, right? Now in tetrahedral, exo attack is favored for both 5 and 6 membered ring. If we are forming 5 membered or 6 membered ring intermediate, as we can see here, so for both of them exo is favored, and for both of them endo is disfavored. So now we have to understand what is exo, what is endo. Now if you see here, this O minus attacks on this carbon. So when it is attacking on this carbon, I minus leaves outside the ring. The ring will be formed this place, and the iodinium ion is going outside the ring. So this is called as exo attack. Whereas if you see on this, when the green light which I am showing, the green arrow which I am showing, attack is happening on this carbon and this goes inside. So when it goes inside, it is called as endo. See, ring is formed overall and the I minus is going inside the ring. This not I minus, the iodine is going inside the ring. So it is called as endo. Now endo is disfavored for both 5 membered ring and 6 membered ring, and therefore attack here will be favored. The green light, the green one is the blue one is favored and the green one is disfavored, which I have shown, because it is 6 endo tet, whereas 5 exo tet is favored. So this goes and attacks here. Now you see here, now this iodine is behind the, away from the viewer. So the bonding molecular orbital is behind the screen. What happens to the anti-bonding molecular orbital? Anti-bonding molecular orbital is exactly 180 degrees to it. So it is towards the viewer. So this O minus will go and attack towards the viewer. So it is attacking from the front. This is also front. So attacks on the front very happily, and therefore this bond and this bond are towards the viewer, whereas iodine goes away from the viewer, and so you get this as exclusive product, and the product is option B. Option B. This is the product. I'll go very slowly. You can read whatever I have said. You can pause the video and watch it. Right, whatever I said is written here. Please go through it thoroughly. Now let's go to next question. The question says the achiral stereoisomer isomers are possible for these compounds. So first of all, stereoisomers means more than one isomer should be possible with different stereochemistry, and one of them should be achiral. So generally if we think it is stereoisomers, that means it is having chiral carbon, then why it is achiral? It's not like that. Many times molecule might be having so many stereoisomers because it is having chiral center, but still some of the stereoisomers among those many stereoisomers can be achiral. Achiral means it will not have a pair of enantiomer. If it will not have a pair of enantiomer, that means it cannot rotate. It cannot rotate the plane polarized light in different direction. See, basically when two pair of enantiomers are there, one pair of enantiomers are there, they are two different compounds. They have to show some difference in property, and they show the difference property in rotating the plane polarized light. So when pair of enantiomers are there, one of them will rotate in left and the other will rotate in right. But among these stereoisomers, some of the isomers will have plane of symmetry. So when it has plane of symmetry, even if you draw the mirror image, you will see that the mirror image is superimposable on the first one, and when it is superimposable on the first one, it means they both are one and the same. So if they both are one and the same, that means they are not enantiomers, and if there are no two different molecules, how can they show two different properties, right? Let us look into each of them. So A. So what it is saying is we need not stick with the stereochemistry what they have shown. We have to draw our own stereochemistry and see. So this molecule is called as alene systems. Okay, so you are having CH3 and CH3. The important thing is this carbon is sp hybridized. Why? Because it has two pi bonds. You can see one pi bond this side, another pi bond this side. So if it has two pi bonds means two unhybridized p orbitals. So the two unhybridized p orbitals are perpendicular to each other. You can see one is in the plane of the board and one is coming, this green one which I have shown is coming outside the board and inside the board. The other lobe is inside the board, and therefore this carbon, imagine if this carbon is sp2 hybridized and this carbon is also sp2 hybridized. So they both will have unhybridized p orbital. So if this p orbital is in the plane of the board, then what happens? These both interact, and because it is interacting in the plane of the board, the CH3, one of the bond is coming outside the board and one of the bond is going inside the board, because shape is trigonal planar. And here what happens? Here the p orbitals are perpendicular. See, I have drawn little bit tilted, but it's not tilted. The thing it means is the green p orbital is coming exactly outside the screen. It's coming out of your board perpendicular to your screen. Okay, similarly this p orbital also coming outside the screen perpendicular, and these two vacant which I have shown as colorless, this is going inside the screen. So now because these both are perpendicular, that means this H and this CH3 is in the plane. Now what happens? Now because of this, see, this molecule does not have any chiral center. You don't see any carbon which has 4 different substituents, but overall there is no plane of symmetry. Why? Because imagine if I am going from here to here, I am seeing hydrogen, but I am going from here to here, I am not seeing hydrogen. Here I am seeing air, nothing is there, because this CH3 is coming outside the board. Similarly, if you see here, when I am coming outside the screen, I am getting CH3, whereas when I go from here inside the screen, exactly opposite, I am seeing air, nothing is there, because these two are in the plane. So it has a asymmetric center. It does not have a plane of symmetry. It does not have plane of symmetry, and therefore it is chiral. Now it has only one chiral center, so it has a pair of enantiomer possible. So you draw the mirror image and you draw a mirror and you draw the mirror image. So when you see mirror, what do you see first? You see your nose first, because nose is coming out. Similarly, this H is coming out, so you have drawn this H. This CS3 is coming out, you have drawn this CS3. When you see your mirror, you see your head on top and leg down, because it will show exactly how it is. So your H is top, so H is being seen, CS3 is down, CS3 is down. And here CS3 is coming outside the board, so you are seeing here also CS3 outside the board, H away from the board, here H away from the board. Now if you see if they are superimposable or not, just turn it around. Just flip it, you understand, lift and turn it around. So when you lift, what happens? This H sits on this H, this CS3 sits on this CS3, but what happens when you have rotated 180 degrees? Please understand, think about it, don't move if you don't understand. You are rotating, you are just, you understand, you are just through the plane of the board, you are just getting it out like that. So what happens? This CS3 goes behind, so this CS3 is sitting on H and this H is sitting on this CS3, and therefore they are non-superimposable, so they both are chiral. And because they both are chiral, now because they both are chiral, there is no possibility of any stereoisomer which is achiral. Only one stereocenter is there, so only two stereoisomers are possible, right? Next question. Oh, so I have not drawn, I will just put it back here and show you. So this is case of atropisomerism generally. Means what happens is these two rings, they find very difficult to rotate, because if this is bulky substituent and this is bulky substituent, imagine these two are in plane, then what happens? This Br come outside the board and this COH goes inside the board. You understand? Otherwise it could have been that this Br goes inside the screen and this COH comes outside the screen. So you get something like this, tuck, 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 and like this. Okay, you get like this. And when you get like this, so one of them will be like that, other case will be the Br will be outside and the COH will be inside. In that case, what happens? That they cannot rotate easily. Not that they cannot rotate, they don't rotate at all. So you have two different molecules and you will see that they are non-superimposable on each other, and therefore they are chiral in nature. They both the molecule is chiral in nature and they both will rotate the light in two different directions. They are pair of enantiomers. But here this COH and Br is not big enough. You need something like PPS3, very big substituent. These two are not able to hold, so this will happily rotate like that. It does not have any barrier. This double bond, single bond is there. So single bond, you know, they can rotate. It will have hundreds of conformers, and therefore no chirality is there. So overall itself this molecule is achiral, right? Talking about this molecule C, now it will have lot of stereoisomers are possible. Like let me show you. It will be something like this H could have been here, this H here, and this OH this side. Now you see that this molecule is not, this is one of the stereoisomers. So there are 8 stereoisomers possible. What I am trying to say is, see here the number of chiral centers. This is one chiral center, this is another chiral center, and this is another chiral center. So 3 chiral centers are there. So the number of stereoisomers possible is 2 to the power n, that equals to 2 to the power 3 equals to 8. So some of them, let me just draw one more for you. So if COH is there, COH, COOH, see these two are different. So there are two different stereoisomers. COH is same, but here OH is on the left, here OH is on the right, and rest all is same. We could have also put, see, both the OH are on the left. I could have put both the OH on the right and both the H on the left. So such things are possible. Now what happens? These are the 8 stereoisomers possible. But what happens in them is, in 8 stereoisomers, at least one of them is like that the molecule has plane of symmetry. And when the molecule has plane of symmetry, asymmetric character is lost, and therefore even if you draw its mirror image, you will see that it is one and the same. That means it cannot have a pair of enantiomers. If it cannot have pair of enantiomer, it cannot rotate light in 2 different directions, and therefore it will be achiral in nature. So look at this molecule. If I draw a plane of mirror image like that, okay, so what happens is, imagine this is a circle, this is a sphere. So I am cutting this sphere into half, this H into half. If I move up little bit, I see carbon. If I move little bit up, I see carbon. If I move little left, I see OH. If I move little left this side, I see OH. So exactly whatever I am moving here on top, I am finding same thing when I am moving down. So it is having plane of symmetry. So when it is plane of symmetry, it is achiral. Why? Because you can draw the mirror image here, and when you draw the mirror image, what happens? H is this side, so H is this side. If you put your hand front, you will see that hand is front with the mirror also. This OH is behind, so this OH is behind, like that. And then what happens, you understand, what I have drawn here is Fisher projection formula. So actually when I draw a single planar line like this, it means this OH and this H is towards the viewer. You are viewing, you are the viewer, that means it's coming outside the screen. Whereas this COH, this whatever is in vertical line is away from the viewer. So this COH is behind your screen, whereas all these horizontal lines are towards you. So if I rotate it like this, just like you catch hold of and rotate it like that, then what happens? Whatever OH is front will go away from the viewer. OH and H which is towards the viewer will go away from the viewer, and this COH which is away from the viewer will go front. Then I cannot check the superimposability. I cannot do that. So in Fisher projection formula, I cannot rotate across the screen like that, but I can let the molecule be on the screen full time, and then I can rotate it something like this. So I can pull so that this COH comes down and this COH goes up, and everything else will rotate. So now what I have done is, I have drawn the stereoisomer, one of the stereoisomer, and then I have drawn the mirror image, right? I said you initially that here both the OH are on the left side. I can also make stereoisomer which are in which both the OH are on the right side. Now the interesting thing is, actually I cannot do that because these both are exactly one and the same, and we will realize it very, very soon. Now see, imagine this one, yeah, this right side one, the B one, I have rotated 180 degrees like that. So this top COH went down and down COH went up, and then what happened to this? This came down. So this OH will also rotate 180 degrees. So it goes down, but OH was on right, it will go on the left. Similarly this one, H was on right, it will go on left. Similarly here this OH, it is going up, it was on right, it goes on the left. Now you see that A and B, they are exactly one and the same, they are superimposable on each other. That means they are achiral in nature, right? Now moving on the last one also, if you draw, I could have drawn like ME behind the viewer and H front of the viewer. If I do that, then there is no plane of symmetry, it will be chiral nature. But if I draw something like this, both ME towards the viewer and both H away from the viewer, then you can see there is a very clear cut plane of symmetry. And if I draw the mirror image, again there will be superimposable. So therefore B, C and D, therefore B, C and D, all of them have possibility of achiral stereoisomers. Okay. Moving on to the next question. The compounds which will show two signals in proton NMR spectrum in the ratio of 3:2. Okay, in the ratio of 3:2. First let us see how many of them will show two signals. That means two hydrogens, this molecule should have two hydrogens which are in chemically different environment. Now let us look at this molecule. It has CH3. So this is in, if I move from this CH3 I get CO, if I move from this CH3 I get CO, if I move here I get benzene, if I move here benzene. That means these both CH3 are in chemically identical environment. So these two CH3 will show one single peak, right? So I have put them as A and A. If I move here, I am moving one position here, I am moving one position here. That means these two hydrogen are also identical. So I put them B. So 2 signals. Now if I move from here, now this hydrogen, see these two hydrogens I have shown in green, this H is in red, and see this blue. Now this blue and green is not same, because this blue, if I move, I am getting one hydrogen. If I am moving here, I am getting another hydrogen. But whereas this green hydrogen, if I am moving one step this side, I am getting hydrogen, but when I am coming this side, I am getting, but when I am moving here, I am getting a carbon. When I am getting a carbon, and therefore B and C are different. That means very clearly this is giving 3 signals, 3 different signals. So we need not look at the ratio of the spectrum at all. This is not the answer. Let us look at B. Now B, these two CH3s are again identical. Now this hydrogen is very different from all 3 hydrogen, because here when I am moving I am getting carbon, when I am moving here I am getting carbon. So this I put as B. Now again this C is different from D. So we are having C and D. So 4 different signals. So you can forget this also. Let us look at this. Now this is having CH3 and CH3, right? So these are different. Now look at this hydrogen. Both of this both of these hydrogens are identical, because if I move one step I am seeing hydrogen, if I move one step I am seeing carbon. Similarly for this hydrogen, if I am moving one step I am seeing hydrogen, one step I am moving I am seeing carbon. See, these both are in chemically identical environment and they both are same as this. So A and B. So it will give two different signals. Now we have to look, is the ratio 3:2 or not. So there are 3 plus 3 hydrogens. So it will give peak of 6, right? 6 hydrogen intensity it will come. And this is how many? 4. 1, 2, 3, 4. 6:4, that equals to 3:2. So because that equals to 3:2, so it is again, because it, so this is what the question was asked, 2 signals with ratio 3:2. So this is the right answer. Molecule D. Now molecule D, again you see this CH3, this CH3 are same. Oh sorry, I have put here A, and then this CH2 and this CH2 are same. So this is put B. So again 6:4. So 3:2. So C and D are the right answer. Okay. Next question, question number 15. The correct sequence of the reaction for synthesis of following molecule is or are. So more than one answer is correct. So you have to get this product. Remember this product, you are having anisole kind of species, Me, benzene with OMe, and then you are having one carbon which has cyclopropyl ring, OH, and of course H is there, which is not seen here. So let us go step by step. So first one, it says you are having 4-iodophenol, you are adding first magnesium, then you are adding cyclopropane carboxyaldehyde, and then you are adding basically methyl iodide. Carboxyaldehyde means aldehyde is there on cyclopropane ring. Let's go one by one. So when you have 4-iodophenol, you are adding magnesium, what happens? Forms Grignard reagent. Magnesium gets added here, so you get MgI. Please remember, it's not Grignard, it's called as Grignard because it is named after a German scientist. So we have to proper name, we have to pronounce properly. So proper now. Now because magnesium is metal by definition electropositive, so it will give electron to the neighboring carbon, and magnesium gets positive, carbon gets negative. So this will attack on this cyclopropyl carboxyaldehyde which is given. So this negative goes and attacks here, this goes and attacks up. So you are on the benzene ring, it attacks on this carbon. On this you are having a cyclopropyl ring, one hydrogen, and O minus MgBr. sorry, by mistake H has come because of this software, but forget that part. And then we are adding the last step CH3I, so O minus goes and attacks this CH3 and you are getting OCH3. Product was, if you remember, it was anisole. OCH3 has to be on the benzene ring, so this is not the product, and here it should have been OH. So let's see option B. Option B, what are there? First you are having cyclopropyl bromide, and then you are adding 4-hydroxybenzaldehyde, and then you are adding methyl iodide. So let us look into it. So first you are having cyclopropyl bromide, you are adding magnesium, it is again forming Grignard reagent. Once Grignard reagent is formed, this negative goes and attacks on this CHO, this comes up and you get H cyclopropyl, you get O minus, and you are getting this benzene ring, and then this O minus goes and attacks the CH3, you are getting this, again you got previous product. See, you should have got here OCH3, but you have not, so this is also not the right product. Option C. Option C says first you are having 4-iodo, so para-iodophenol, then you are making Grignard reagent, then you are reacting it with cyclopropane carboxyldehyde, right? So let us see step by step. So first you are having 4-iodophenol and reacting with CH3I. So oxygen has lone pair of electron which goes and attacks the CH3, this goes and you get OCH3 and I. Then you are adding magnesium, so it forms Grignard reagent, then you are reacting with carboxyldehyde. So you know this negative charge is there on the carbon, this goes and attacks the positive polarized carbon of the carbonyl group, and this goes up and you get O minus MgBr, put water you get OH, and this is what was the product. Remember, anisole kind of product, and this carbon had OH and you are getting this. So this is the right product, C is the right option. Fourth one it says you are having cyclopropyl bromide magnesium. So of course first one is Grignard reagent, then you are reacting with methyl 4-methoxybenzoate, so it is ester. On ester Grignard reagent attacks twice, first it will form carbonyl and again it will attack till it forms alcohol. So let us see how it is formed. So first you are having cyclopropyl bromide, we are reacting with magnesium, so you are getting cyclopropyl magnesium bromide, you are getting the Grignard reagent. You know very well, this gets negative charge, magnesium is having positive, so this goes and attacks on this ester, so the bond goes up, electron goes up, pi bond, and then it comes down and this OMe leaves, you get a carbonyl in the first step. Second step, again as I said previously, Grignard will again attack, it will again attack here and this goes up and you are getting this. So this is also not the product, so the answer is option C again. Okay. Question number 16. The organometallic reagents among the following are. So this is a damn simple question. So first one is lithium divinyl cuprate. So it is R2CuLi, that kind of species. Okay, R2CuLi, where R is vinyl group. So vinyl is nothing but like this group. Okay, so this is Gilman's reagent. So of course this is the answer. This is LDA, lithium diisopropyl amide. So LDA is just a base, it's not a reagent. Similarly, this one is potassium tertiary butoxide, is again a very powerful bulky base, non-nucleophilic. So this is again O minus K plus, and you are having tertiary butyl here. So this is again not a reagent, just a base. And this one, you know, this is a Grignard reagent, isopropyl magnesium iodide. So option A and D are the right answer. Okay, option A and D are the right answer. Let's move. Question number 17. It says the total number of tautomers possible for 1 and 2 together. So first we have to understand what is tautomers. In tautomers, what happens? First it exists in solution generally, and then here there are many interchangeable forms because chemical bonds are rearranged simultaneously. Many chemical bonds are rearranged. Most important thing is here atom actually shifts. When you talk about chemical structures, when you talk about resonance, we only show electrons moving, atom does not move. But in tautomerism, atom moves. See, I will show you here, hydrogen is moving. Okay, after some time I will show you. And apart from that, tautomers are neutral and it follows octet rule. So this is very simple question, but it was very time consuming. So see here, the octet rule has to be followed. So NH, first I broke this. So what I am showing is this single bond is moving inside. That means hydrogen is going out as H plus, and this pi bond comes here and this comes here, this becomes O minus, and this O minus picks up this proton, and what you get is OH here and you get double bond here. So this is the first tautomer. And then what I have done, then I have put this NH, this also I have broken, this goes up, this comes here, you are getting the third tautomer. And then again benzene ring is also involved. So this OH is there, so this moves in, so you get a double bond here, this moves here, you get a double bond here, this moves inside, and then hydrogen picks up this proton. Sorry, this benzene ring picks up this proton and you are getting CH2. So this is another one. Then you can keep moving on each of the benzene rings. So this moves in, this comes up, and double bond comes here, you get here, last you cut here, you get this. Similarly, after that you can start from here, you stop it here, then start moving this OH bond, this comes inside, you get a double bond back here, and this moves in, this comes here, and this moves here, and you get a hydrogen here. So this is another tautomer. And again similarly this moves, it comes here, and you get another tautomer, another tautomer. So I have written this as A, B, C, D, E, F, G, H, I. Then next one, now second one I have taken, I have started them with letter J. So only problem is here Me is there. So when Me is there here, had I shown attack either from this or from this, it would have been same because they both are side. But here it is different because Me is different from the benzene ring. So it will have here benzene will not be involved, but in that case it will have one more stereoisomer one more tautomer more compared to the previous one, not counting the benzene ring, just counting the double bond. So see here I am showing this double bond here and you are getting this bond here. So N double bond and you get OH here, and what I am trying to say is this, look at this, okay. So if I show here this double bond here and OH here, so these two are two different things, which was not the case in previous one. So first you move here, you get OH here, and then second you move here, you get OH here, and then you show the benzene ring. So this double bond comes here, this moves here, and this moves here, and you get here, you get this. Then you keep showing the benzene, and then I was showing back normalization of benzene ring. So this comes here, this comes here, this comes here, and this comes here. So you get same I which was here. Therefore I have put them both as same name so that we don't get problem in counting. And then this comes here, and this pi bond comes here, this OH bond breaks here, comes here, and you're getting this P. So total number of A to P you can count, it is coming up to 16. So total number of tautomers possible are 16, right? Fine. Let's go to the last question. It says the total number of head to tail isoprene linkage in the following molecule. So this is example of terpene or terpenoid. Terpenes are just hydrocarbons, terpenoids will have OH or double bond carbonyl groups are there, right? So in them isoprene unit is there. This is what is called as isoprene. So 5 carbons are there, 1, 2, 3, 4, 5. So one has isopropyl part and the other ethyl part. So isopropyl part, you can see here it looks little bit like head, so this is called as head, and this ethyl part looks like tail, so it is called as tail. So you have to look here how many, what's the question? The question says how many head to tail linkages are there. So look here, this molecule. So here this is the head, cyclopropyl part, this is the ethyl part, so this is the tail, and it is joined with this part, this is the cyclopropyl part. So tail to head, or head to tail, this is the head to tail arrangement. Now similarly here when you come, this is head, so this has to be tail, and here again cyclopropyl is there, so this is the head to tail linkage is there. It comes here, becomes 5. Interesting thing is stops here 5, you have to stop at 5. 1, 2, 3, 4 and 5. Whenever 5 carbons happen, 5 carbons you count, that is one isoprene unit. Come to here. Now here it starts with the ethyl part, and the cyclopropyl part is this side. So this part is head and this part is tail. So this is tail to tail linkage, which we don't want. What we want right now is head to tail. Similarly here, if you see, we saw this was head and this is again tail, because this is head 3, 4 and 5. So this is again head to tail, and this is head, you can see this cyclopropyl, and this is tail, so again head to tail. So total number of head to tail are, let us count. Head to tail is 1, 2, 3 and 4. So the answer is 4. That's it for today. Thank you very much.